All right, yesterday we got our introduction to NMR spectroscopy. We said that NMR spectroscopy is used to look at the nuclei of atoms that have either an odd number of protons or an odd number of neutrons. And when they have that, the charges inside the nucleus actually spin. And when they spin, they make a magnetic field. And so NMR spectroscopy is used to study the magnetic field that's created when there's a spinning charge. In particular, we started discussing the number of signals we can anticipate from NMR spectroscopy. The first one we said was that nuclei in the same chemical environment have the same resonant frequency. It shouldn't be resonance frequency. Sorry about that. And so in this case, if we think about proton A and proton B on dichloromethane, if we imagine ourselves in those positions, we're in the exact same chemical environment. So HA and HB, both of those protons, will actually show up as one shared chemical signal. So if we were to look at the NMR spectrum for dichloromethane, we would only see one peak for both of those protons. We said if we look at something like dimethyl ether, that those methyl groups will spin around like helicopter blades, and they will also occupy the exact same molecular space. So again, we'll only see one signal for all of the HA protons on dimethyl ether. However, we left off by saying that if we're in different chemical environments, that we'll actually observe different resonant frequencies. Sorry, I keep on saying resonance frequencies when that's not grammatically correct. So let's take an example here, and I'm going to look specifically at ethanol, my favorite alcohol. Why? It's the only one you really want to drink, right? All right, some people got that joke. Maybe it's better that a lot of you didn't. All right, so we've got a bunch of protons coming off of here. And if we think about this, we've got the terminal methyl group. And then we've got the methylene protons in between. How many unique sets of protons are on this molecule? Let's kind of work our way right to left and ask ourselves. If we're looking at this proton over here, HA, are there any other protons on the molecule just like it? No, so it'll have its own signal. There are no other protons in the molecule just like the proton that I've labeled as HA, so it will only have one signal. What about the next one over? I'm going to label these blue. Is there any other proton like HB? Where's the other proton just like it?
Oh, no.
Right next to it, right? So it's on the same carbon. So if we look at HB, one's just sticking towards us and one sticks away from us, but they're sharing the exact same chemical environment. So we'll have another signal for the protons that I've labeled as HB. What about the methyl group on the end? Are all of these the same?
No.
What do you think? If we think about a methyl group like a helicopter blade, yeah, they're all going to be the same. Theoretically, if we cooled down the methyl group so that it doesn't rotate on the scale of the NMR anymore, then we actually would see these as separate protons, but the reality is room temperature is enough to make a methyl group spin like a helicopter blade. So these are all going to show up as distinct peaks. So if we look at ethanol, we've got 3 proton signals. And then if we think about the carbons, is the carbon on the left the same as the carbon on the right? No. So how many carbon signals will we observe? 2. And the question is, are we observing carbon 12 or carbon 13? 13, right? It has to be an odd number to be observable by NMR. So in this case, we're observing only carbon 13 signals. And we mentioned during our mass spec segment that carbon 13 is present at 1.1%. So 1.1% of all carbons are going to be carbon 13. So when we're running carbon NMR, it actually takes much, much longer to acquire a spectrum than it does with something like a proton NMR. Protons are everywhere, right? We can detect those really easily because they're in such high abundance. But with carbon 13, we actually have to run it quite a bit longer in order to pick up that 1.1% that exists naturally. All right, let's do another one. This time I'm going to do an aromatic ring. And again, I want to label or determine how many unique sets of protons there are and how many unique sets of carbons there are. So I'll give you guys a couple minutes to work on this, and I'm going to draw in all of the hydrogens so that we can see where they all are. All right, let's start with the methyl group on the top. Are there any other protons that are exactly like the methyl group proton I've labeled HA?
Yes.
Which ones?
Bottom.
So you're saying this one down here?
I agree.
So are there only 2 protons in that set?
No, there's 3. 6 total.
6 total, right? So if we think about this, both of these methyl groups are in the same chemical space, that same chemical environment. They both spin like helicopter blades. So all of these HA protons are going to share the exact same signal. All right, now let's move down to the next one. I'm going to label this HB. Are there any others like HB? Which one? Or which ones?
Top left.
Top left? Okay, so I'll label this HB. Are there any other like HB?
Yes.
Yeah, the remaining 2, right? So if we think about it, even though they're not on the exact same carbon, they're all in the exact same chemical environment. If you're pretending that you're these protons labeled HB and you look around, if you look behind you, there's going to be a methyl group, and if you look in front of you, there's going to be another proton on the aromatic ring. So if we look at this molecule, there will be 1 proton NMR signal, or sorry, 2 proton NMR signals, 1 for HA, 1 for HB. And then how many carbon signals will we have?
2.
So let's ask ourselves, all right, let's look at this green carbon on the top methyl group. Are there any just like it?
Yes.
Which one? Yeah, the other methyl carbon, so down here. So that's 1 unique set. What about this carbon? Is there any just like it? Yep, that one. And what about, let me do blue. What about this blue carbon? Are there any other carbons just like it? Yeah, the remaining carbons, right? So how many unique sets of carbons do we have? 3. So let's take a look at what the spectrum would look like for this molecule. This is actually called paraxylene. We'll talk a little bit more about naming aromatic molecules when we get to that section. But if we look at the proton NMR, the scale is on the bottom. And the scale is in the units of ppm, or parts per million. And oftentimes you'll see it drawn with that lowercase delta signal. And really what this refers to is something called your chemical shift. Sorry, let me try to make my lines straighter here. That's a little better. All right, and the scale for this is a little bit different. The 0 on the scale is going to be on the far right. And then if we go over all the way to the left, proton NMRs typically only observe signals up to about 15 parts per million at the very highest. Sometimes you might see it a little bit higher, but 15 is already at the extreme end. And so we could put in hash marks and we can say, all right, we've got 5 ppm there, we've got 10 ppm there. And if we're looking at the proton NMR, we would see a signal probably showing up. I'm going to label it in blue to distinguish it from our axes. You might see a signal showing up around there, and you might see another signal showing up around there. So we can see the 2 signals for this compound that we predicted. They're showing up in different spots because they have different chemical frequencies. So if we look at HA and HB, it's going to take a different frequency of pushes to knock it off the axis that it likes to spin on. All right, let's do,
Why, I don't understand why they're, well, with this one right here.
so if we think about this, let's label these. Basically, all we need to know at this point is that we've got two separate proton NMR signals.
Okay.
We're going to practice interpreting the chemical shifts and what they mean a little bit later, but for right now, all we're really concerned with is how many signals should we anticipate in our NMR spectra or spectrum. All right, let's do one last example one, and then we'll use our problem of the day as a class activity. This one's going to be a little bit trickier. So we've got an aromatic ring attached to a 5-membered ring. And I've got 2 chlorines here. And then I've got 1 chlorine here. How many proton signals should we pick up in this compound? I'll give you guys a minute to think about it. But try to imagine yourself as the proton, kind of dangling off the molecule, and imagine yourself looking around, and then ask yourselves, are there any other protons with the same vantage point that I have? I'll go through and draw in all the protons too. Oh, shoot. Does anybody have a guess or an idea how many proton signals we should maybe see? I heard it's 6.
For the hydrogens,
For the protons only, not the carbons.
3.
This one's a little tricky, so let's take a look at it. All right, so we've got, I'm going to label this HA. If it's looking kind of forward and to the right, it runs into 2 chlorines. Are there any other protons in that exact same chemical environment?
Yes.
What about the one on the bottom?
Yes.
It looks forward and it only sees 1 chlorine. So the one on the bottom is actually different, right? So if we think about the one on the bottom, if it looks forward, it's only seeing 1 chlorine, so it's in a different chemical environment. It doesn't have the same vantage point. So we've got HA and HB labeled. What about the other aromatic protons to the left? Are they the same or different? So let's label this one C. C, if it looks all the way past proton that's labeled B, it sees 1 carbon. If we look at this proton up here, which I'll label HD, it looks past proton A and it sees 2 carbons. So it's got a different vantage point, right? Or chlorine. Did I say carbon? Sorry. If it looks past proton A, it sees 2 chlorine atoms. If we're looking at proton C, it looks past proton B and it sees only 1 chlorine atom. So we've got 4 different aromatic protons. What about this proton here? This will be E, I guess, if we're going alphabetically. Are there any other just like it?
No.
No, there are no other protons attached to a carbon with a chlorine. What about proton F? Are there any just like it?
No.
This is a little weird to think about. If we're looking at the proton that I've labeled F, it looks behind itself and it's kind of cis to proton that I've labeled E, and it's kind of anti to the chlorine there, and then it looks to the other side and it sees 2 chlorines. If we look at the top one that I'll label G, G is kind of cis to that chlorine as opposed to F where it's trans to that chlorine. So they're actually in different chemical environments, so you have to look at this using kind of a 3-dimensional mindset, right? If we're looking at G and F, they're not in the same chemical space. And this is something that's confusing for a lot of people. And these protons have, their own special name. Oftentimes people mix them up and they think that they'll share one signal, but these are actually diastereotopic protons. So in this case, if we're counting how many different protons we've got 1, 2, 3, 4, 5, 6, 7 different proton signals. Diastereotopic protons are just simply protons in different chemical environments, and they're called diastereotopic because they're not superimposable in the mirror plane, right? If we think about this, if we switch one with a deuterium, we'd actually have a set of diastereomers in there. So diastereotopic protons are often the wrench that's thrown in this game, and we have to pay attention to the three-dimensional space of these molecules oftentimes. So what we're going to do next is we're going to pull out our problem of the day 15. And we're going to go through and do this exact same process for all of these compounds, but I want you guys to take special care to pay attention to the three-dimensional space, especially with compounds that aren't planar. All right, let's reconvene here and try to figure out what's going on with the signals here. How many proton signals do you think are in the first compound on the left? So what I'm counting is I've got one proton here that's not the same as this proton here, not the same as this one, not the same as this one. And then we know the methyl group protons are all going to stick together in one group. So I'm counting 5 signals. How many carbon signals are we going to have in this compound? Let's go through and count. We've got 1, 2, 3, 4, 5, 6, 7, 8. So we should have 8 carbon signals in that first compound. All right, what about the next compound? This one I think is actually surprisingly simple. Raise your hand if you think you have a guess. How many do you think, Kareem? For the protons? 2, right? So if we look at this proton coming off here, it's got an equivalent proton on the opposite side, right? If we look at this molecule, there's actually an internal plane of symmetry going smack down the center, so the proton on the right is going to be in the same chemical environment as the proton on the left. They're in the same chemical space. And then if we look at these protons down here, same thing. So we've got 2 sets of chemically equivalent protons. All right, how many carbon signals should we have? 3, right? Because of that internal mirror plane, the ones on the right side of that mirror plane are going to be in the same chemical environment as on the left side. So we've got 3. All right, now let's take a look at the next compound over to the right. Do you guys want some time to work on that? Okay, I'll give you some time to work on the next ones, and then we'll reconvene again. All right, if we look at the next one over, it's an alkene. If we look at these protons here versus over here, are those methyl group protons going to be equivalent or different? Different, right? We said one's going to be cis, one's going to be trans, so they're actually in different chemical environments. So each of those will be a unique signal. What about this proton here? Are there any others like it? Nope. So that'll be our third set. What about these protons here? Are they the same or are they different? Are they?
Yeah. One had a double bond and the other's not.
It's important to remember that they're not pointed like that. One's actually more of a wedge. The other one's a dash. So they are in the same chemical environment. One's just sticking towards us and one's sticking away from us. So these are a unique set.
Okay.
If we had stereochemistry nearby, then they would be in a different chemical environment, but there's no stereochemistry nearby that would affect the chemical environment. All right, so this would be its own unique set. So we've got 1, 2, 3, 4. What about this proton here? Are there any like it? Nope, so that's its own unique one. What about this methyl group on the top versus that methyl group on the bottom, are they in the same or different chemical environment? Same. We can think about an isopropyl group spinning like a helicopter blade too. So these are actually going to be in the same chemical environment. So if we go through and count these, I'm counting 1, 2, 3, 4, 5, 6 different proton signals that we should observe. Is that right? It's kind of a rhetorical question, I guess. All right, let's look at how many carbons there are. We said that this methyl group is in different chemical space than that one, so we've got 2 unique signals. This carbon's unique, so that's 3. This carbon's unique, 4, 5, 6. What about these last 2 methyl groups? Are they the same or different? They're the same, so how many carbon signals? There should just be 7, right? Because we know that these last 2 carbons are actually going to be in the exact same space, right? Because if that isopropyl group's spinning around like a helicopter blade, both of them have the equal probability of being in the same chemical environment, right? Just like a helicopter blade, one rotor at one position in time has the equal probability of the other rotor being in the same chemical environment or the same space.
Wait, isn't that the same?
So we've got 1, 2, 3, 4, 5, 6, and then the circled 2 would be 7. Yeah. This does take a lot of practice, which is where sapling comes into play. If you do the sapling problems regularly, you'll be able to pick this up really, really quickly.
Is this chapter 16?
This is chapter 16, yes.
Oh.
All right, now let's look at the cyclohexane ring. And this time I'm going to help you guys out. The key, I think, with a lot of these when you're looking at chemical space is to do a model. So if we have a cyclohexane, what conformation is it usually in? Chair, right? And if we've got a tert-butyl group coming off, does that tert-butyl group want to be axial or equatorial? So it's going to be 99.9% equatorial. Very, very little will be axial. So we really won't observe the axial position by NMR. So if we look at our model, it looks something like this, where the tert-butyl group is axial. And this tert-butyl group can spin like a helicopter blade. So knowing this, let's try to figure out how many proton signals and how many carbon signals there would be. For the tert-butyl group, are the methyls group protons going to show up the same or different? Same. So that will be one set. All right, so let's circle that on there. We know that this will be one set. Whoop. Let me do a better job circling. All right. What about this proton coming off here? Is that going to be the same or different? Different, right? There are no other protons on the same carbon that a tert-butyl group's coming off of. All right, now let's move over. And if we look at this one, we've got one that's a proton that's axial, meaning it's sticking up. Are these the same or different?
Same.
They're going to be the same, right? So if we look at this proton is in the exact same chemical space as this proton, right? They're both sticking up. What about the equatorial ones? Are they the same or different? They're the same as each other, right? So the axial ones are going to be the same. And then the equatorial ones will be the same. So let's keep a tally here. We had one for the tert-butyl. We had one for the proton coming off of the carbon where the tert-butyl was attached. We had one for the axial, one for the equatorial. Now let's move one carbon away. Now the axial groups are pointed down. Are those the same or different? They're going to be the same, right? So we've got another set here where these are the same.
Why aren't they the same as the other one?
Because if we look at this one, the axial groups that are closer to the tert-butyl, if we think about it, they're cis to one another. If we look at the axial groups one carbon away, they're actually trans to one another now. So they're in a different chemical environment.
No, I mean, like the three that are sticking up, why aren't they all the same?
So if we think about this one's much, much further away from the tert-butyl group.
Yeah,
So
but there was another one like that. You said, I just asked you if you count the carbons. If you look at what's next to it, you said to go even farther, but then you did it on that one.
Yep, so these two, if we look at it, there's an internal mirror plane going down the center of the molecule. This one, that carbon on the very opposite end is in the mirror plane. The other axial positions are out of the mirror plane. So we've got these axial protons, one carbon further away, they're unique. Another set of equatorial protons are unique. And what about the end that's on the opposite side of the tert-butyl group? Are they the same or different? Different. We've got one axial and one equatorial. So let's go through and count all of these protons, because I know when we start getting into more complex three-dimensional space, it gets super challenging to see this, which is why model kits can help you out a lot when you're doing NMR problems. So we've got one for the tert-butyl, one for the proton that's attached to the carbon next to the tert-butyl, one for the axial, one for the equatorial, one for the axial, one for the equatorial, one for the axial, one for the equatorial. So I'm counting 8. Is that what other people got?
No.
Keep on practicing these. These take a while to see, especially with things like chair conformations. How many carbons? The methyl groups are going to be the same, right? What about the carbon that's the center of the tert-butyl group? Are there any others like it?
Yes, on the bottom.
This one? Or no, so that's going to be its own unique carbon. So we've got 1, 2. Carbon further in is unique, but then we've got a plane of symmetry.
Yeah.
7, 8, 9.
Wait a minute.
So let's go through it. I'm going to erase this so we can see it more clearly. All right. Let's make sure we can hear. So all those methyl groups, right, that I just highlighted, that will be 1. So I'll start with a 1. Next one in will be its own unique one, so that's 2. Next one in will be 3.
Why isn't the bottom one the same as that one?
Because the one I just highlighted is attached to tert-butyl group, the other one's not. All right, now I'm going to go down the right side. We've got this one, which is 4.
Isn't that the same as the one on the left?
Exactly. So these two really darkly shaded green ones, those are going to be the same. Next one down, these two are going to be the same, so that's 5.
And then 6.
And then 6.
Oh, no, 9.
Did I say 9? Oh my goodness. 1, 2, 3, 4, 5, 6. It's been a long day, guys. Sorry. It's a good thing we're not putting this on the internet or anything. All right. Let's do the next one.
I don't want to. I want to do it. Okay, so,
Right? You think counting's hard until you have to do it, and then you're like, oh, wait. Did I say 5? Did I say 4? I'm getting really confused now. So if you need to, do the tally system or label them as protons A, B, C, D.
I used to be like Megan, just saying approximately.
Approximately. Scientists don't like to use the word approximate when it comes to spectroscopy, I guess. A ballpark of a dozen or so, you know. All right, let's take a look at these methyl protons. Are there any like it? No. So we've got 1 set for that methyl. What about this proton down here? Are there any like it? No. So that'll be 2. What about this one? No. So that'll be 3. Next one? No. That'll be 4. There we go. Here, I'll label this CH3. And then what about these two?
no. Just keep saying no. Because I'm the one that you know.
Are they the same or are they different?
Oh, that was
All no stereo centers.
There's no stereo center, right? So these are actually going to be the same. What about the next two? Are they the same or different?
same.
So these will be the same, these will be the same,
Same. No, different. Different.
these will be the same
Like
actually.
the oxygen and then there's carbon. That's what I'm talking
So
about.
I'm going to help you guys with this. But let's go through and finish doing the tally. So we had 1, 2, 3, 4, 5, 6, 7. So again, this is where the model kit comes in. Don't get discouraged. I know it's tricky. So if we look at the carbons that are on this cyclohexane type ring, is it really a cyclohexane?
No.
We've got an sp2 carbon, sp2 carbon, sp2, sp3, sp3, sp3. So we need to change 3 of these vertices. So I'm going to swap them out and put in an sp2 chunk here for 3 of these vertices right next to each other. And this one's a little funny to look at. Some people call it kind of an envelope conformation. It'll make more sense when we see it, because those 3 sp3 hybridized carbons are going to be planar, right? Trigonal planar. So if we look at those 3 carbons, they're going to be in the exact same plane. The remaining 3 are tetrahedral, which means we've got like this envelope flap on the other side. It takes very, very little energy to flip an envelope flap compared to a chair conformation. A lot less energy. So if we're looking at this in the NMR, this envelope flap is actually just going to be flipping up and down, up and down, up and down, which, like a helicopter blade, means that these protons that are attached to each carbon are going to share the chemical environment, right? They're going to be in an equal probability of being in that same chemical environment. So sometimes these get really tricky. I thought that one was the most challenging question on here. How many unique carbons are in this molecule? That one's a little easier now that we've narrowed it down. How many carbon signals would we anticipate? So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's no symmetry in this molecule, so we're going to end up counting all of the carbons in it. So we can gain a lot of information from NMR spectroscopy just from the number of signals that we're observing. I really recommend going through sapling and practicing this. Pull out your model kit if you're having trouble seeing the diastereotopic positions, and see if you can play around with some of those until you feel pretty confident in it. This is the most important thing when you're analyzing an NMR spectrum, is to actually just anticipate the number of signals and know what that would correspond to for a given molecule. All right, the next one, you'll be happy to know, is easier.
All right. And this is all on the quiz, Thursday.
We'll talk about the quiz later. Don't worry about the quiz right now.
2 days away.
All right, so now we've determined the number of signals. The next step after you've determined the number of signals is to determine the relative size of the signals. So let's take an example here. And I'm going to stick with the paraxylene example because I like it. We said that we had a bunch of different protons coming off of here. I'm going to label all of these as either HA or HB. And we said the methyl groups are all going to have the same protons, so we'll label these all HAs. Then we'll label this as HB. Sorry, I'll slow down. And then what I'm going to do is we said we would have 2 1H NMR signals. So this is exactly what we had in our notes before. Right, so we'll get a signal for the HA protons and then a signal for the HB protons. So we should anticipate seeing 2 signals. And then we went through and we actually drew the anticipated NMR spectrum. We're going to practice this a lot more. And we said that the units was going to be in ppm. The scale from right to left will go from 0 to about 15. And then I said that there would be some peak kind of close to 2 ppm. Oh, that's kind of a fat peak. Let me try to fix this. All right, so we've got a peak right around 2 ppm. And then we've got another peak right around 7 ppm. And so when we get this spectrum, what we can do is we can actually tell the computer, I want to know the area underneath each of these peaks, right? So what we call this in spectroscopy is just integration. So similar to mathematics, we're trying to find the area underneath the curve. And so what the computer will do is it will split out a curve, and it will give you the area of the peak. And then the other one over here will give you the area of that peak. In this case, we can actually tell the computer, all right, I want the one on the left to be equal to approximately 4. And then the computer will tell us, well, if you're setting that area to 4, the relative area of the one on the right will be approximately 6. So which peak do you think corresponds to which proton? Or proton set, I should say.
A.
So the one on the right is which one? A, right? So if we look at this one, the one that integrates as 6 must be HA. Right? Because there are more protons, that signal is going to show up more intensely, and we can actually measure the area underneath the peak to give us an idea of the relative ratio of protons for each set. Conversely, this one must be HB, right? Because if we look at HB, there are only 4 protons in this set. So if we look at the ratio of protons for HA to HB, it's going to be a 6-to-4 ratio. Another thing that kind of confuses people, I'm going to scroll down here. The ratio for HA to HB we said is equal to 6-to-4, right? Based on our graph. What if I set it to 600 for HA? What would the integration be for HB? 400, right? It's just a ratio. People get really hung up on the numbers, and they say the integration tells us the exact number of protons. Not entirely. It tells you the relative ratios of protons, right? We can set the integration to be whatever arbitrary number we want it to be, but that ratio still needs to hold true. So it could be 600 to 400. It could be 3-to-2. All this is telling us is the ratio of protons that we have to other sets of protons in the same molecule. So the ratio of protons in each unique set. Oop. Pretty simple concept, but it's really, really valuable, right? So just from this example spectrum that we drew up here, we've already identified which signals belong to which protons, right? So very valuable tool. Are there any questions with integration? No? All right, so that's one of the easiest ones. The next one is looking at signal multiplicity or signal shape. This kind of gets abstract, but I'll try to define it the best way I can. And it's that nuclei can be spin up or spin down. And depending on the spin state, it will interact with neighboring protons differently. Let me actually change that. It will result in spin-spin coupling with neighboring protons. Or neighboring nuclei. Normally, organic chemists are interested almost exclusively in proton NMR spectroscopy and carbon NMR spectroscopy. Occasionally, we may do different sorts of spectroscopy, but in this course, we're only going to be focusing on those two nuclei. So let's take an example here. What I'm going to do is I'm going to just have two basic carbon atoms, and I'm going to label this one as HA and the one on the right HB. And I'm just going to throw off lines here. It doesn't really matter what's coming off of those other positions. Right now, we're only interested in HA and HB. So let's assume we're looking at HA, and we're examining the signal that's resulting from HA. It's got a neighboring proton nearby, right? HB. HB can be spin up or spin down, right? So the spin state of HB affects HA. And that is to say, HB could be either spin up, that's one option, or it can be spin down. So I'm going to label this HB. It's actually an equal probability of this being in the spin up state or the spin down state. So in this case, we're looking at a 50-50 ratio of spin up to spin down. This will actually cause the signal for HA to be split into a 50-50 ratio of two signals. So instead of being one solid peak, it will actually split out into a doublet. So let's take a look at what the peak for HA would look like. If we look at the peak for HA, it'll look a little bit like that. So instead of one peak, the neighboring proton, that HB proton, could be in spin up or spin down, which will affect it. So we'll get two different potential peaks for HB, and this is called a doublet. Oftentimes people, when they're referring to a doublet, they'll just say D, because you see doublets very, very frequently in NMR. All right, let's take a new one. So this was our first example. Oh, shoot, we're running out of time. Sorry, guys, I completely lost track. Hang on to your problem of the day. It'll be an in-class activity for tomorrow, and we'll go through it together.
Can we do like